Some stars are special. Some stars are almost identical twins to our own Sun. And around these stars we have found worlds that might, just might, harbour life. One such star is Kepler-452. Hidden in the constellation Cygnus, this star is so remarkably similar to our Sun that it sends shivers down the spines of astronomers. It burns at nearly the same temperature. It radiates the same golden light. It is almost the same size. If you could somehow transport our Sun 1,800 light-years away and replace it with Kepler-452, you would barely notice the difference. This is not science fiction. This is reality. And this reality raises a profound question. If this star is so similar to our Sun, could the planets around it be similar to Earth? But here is the catch. Kepler-452 is invisible to your naked eyes. You cannot walk outside tonight and point to it in the sky. It is too faint, too distant, drowning in the cosmic ocean of starlight. You need a telescope to even glimpse its existence, and that distance, that 1,800 light-years separating us from Kepler-452, is almost incomprehensible. Light, travelling at 300,000 kilometers per second, takes 1,800 years to reach us from that star. The light you would see through a telescope tonight left Kepler-452 around the year 225 CE, when the Roman Empire still dominated the Western world. Now imagine trying to travel there. With our current technology, our fastest spacecraft, the journey would take approximately 30 million years. 30 million years. Let that sink in. Modern humans have only existed for about 300,000 years. Civilization as we know it is merely 10,000 years old. The entire span of recorded human history would fit more than 5,000 times into the duration of that journey. You, your children, your grandchildren, stretching out for over 1 million generations, would live and die before that spacecraft ever reached Kepler-452. Yet despite this crushing distance, despite the impossibility of ever setting foot on worlds orbiting that star, we study it obsessively. Why? Because Kepler-452 represents hope. It represents the possibility that we are not alone. Sun-like stars are the prime candidates in our search for extraterrestrial life. They burn steadily for billions of years, providing the stable energy needed for life to evolve. They are not too hot, not too cold. They do not flare violently like red dwarfs, stripping away planetary atmospheres with bursts of radiation. They are, in every sense, Goldilocks stars. Just right. And Kepler-452 has at least one confirmed planet. That planet is designated Kepler-452b. Think about that designation for a moment. The B means it was the first planet discovered around that star. The star itself gets the letter, and each planet discovered around it gets a letter in sequence. Kepler-452b, a world orbiting a star almost identical to our Sun, a world we have detected from 1,800 light-years away, a world that might change everything we think we know about life in the universe. These discoveries did not come from luck or chance. They came from one of the most ambitious scientific missions ever conceived, NASA's Kepler mission. Launched in 2009, the Kepler Space Telescope stared at a single patch of sky for years, watching over 150,000 stars simultaneously, waiting patiently for the telltale dimming that occurs when a planet passes in front of its star. It was looking for transits, those brief moments when a distant world blocks a tiny fraction of its star's light. And it found thousands of them. The Kepler mission revolutionized our understanding of planets beyond our solar system. Before Kepler, we knew of only a few hundred exoplanets. After Kepler, we discovered thousands. We learned that planets are common, not rare. We learned that nearly every star in our galaxy hosts at least one planet. We learned that worlds come in bewildering varieties, gas giants larger than Jupiter, orbiting closer to their stars than Mercury orbits our Sun, rocky super-Earths with crushing gravity, ice worlds, lava worlds, planets orbiting binary star systems like something from a science fiction movie. But among all these discoveries, certain planets stand out. Planets like Kepler-452b, planets like Kepler-22b, another world we will explore soon. These are not just any planets. These are worlds orbiting sun-like stars at distances where liquid water could exist on their surfaces. These are worlds in the habitable zone. These are worlds where life, as we understand it, could potentially take hold. Sun-like stars expand humanity's search for life beyond Earth because they offer the best chance of finding conditions similar to those that allowed life to flourish here. Earth is our only example of a living world, our only blueprint. We do not know if life requires the exact conditions we have here, but it is the only template we have. So we search for Earth-like planets around sun-like stars, hoping that the cosmic recipe that worked here might have worked elsewhere too. Kepler-452 is one of those precious targets. Among the 400 billion stars in our Milky Way galaxy, this star stands out as a near-perfect analogue to our Sun, and it has a planet that orbits at a distance remarkably similar to Earth's orbit, a planet that receives sunlight similar in intensity to what Earth receives, a planet that might, in some alternate version of cosmic history, have evolved its own story of life. But space is filled with mysteries and dangers we are only beginning to understand. Distance is just one barrier. There are questions we cannot yet answer about Kepler-452b. What is its atmosphere made of? Does it have water? Does it have a magnetic field to protect it from cosmic radiation? Is its surface solid rock, or is it covered by endless oceans? Could anything live there? And if something does live there, would it recognize us as kindred, or would we be so alien to each other that communication would be impossible? These questions drive us forward. They fuel our telescopes, our space missions, our dreams of reaching beyond our small blue world. Kepler-452 is not just a star. It is a beacon calling us into the cosmic ocean, reminding us that our Sun is not unique, that Earth might not be alone, that the universe might be teeming with life, waiting to be discovered. The discovery of Kepler-452b and other exoplanets marks a turning point in human history. For thousands of years, we wondered if other worlds existed. Now we know they do. For thousands of years, we wondered if we were alone. Now we are closer than ever to answering that question. The stars beyond our Sun are no longer just points of light in the night sky. They are suns with their own families of planets, and some of those planets might be looking back at us, wondering the same thing. Now comes the hard truth. Discovery is not the same as salvation. Finding a potentially habitable world does not mean we have found a new home. It means we have found a new set of questions, a new collection of unknowns that could either offer hope or deliver crushing disappointment. Let us turn our attention to another remarkable world, Kepler-22b. This planet holds a special place in the history of exoplanet discovery. It was the first planet ever confirmed to orbit within the habitable zone of a sun-like star. Think about the weight of that achievement. The first time in human history we could point to a distant world and say with confidence, liquid water could exist there. Life, as we know it, could survive there. This was not speculation. This was science backed by data, by measurements, by mathematics that did not lie. Kepler-22b orbits its star at a distance that places it squarely in the Goldilocks Zone, that precious region where temperatures allow water to remain liquid rather than freezing into ice or boiling away into vapor. One complete orbit around its star, 1 year on Kepler-22b, lasts 290 Earth days. Not quite as long as our year, but close enough to suggest stability. Close enough to suggest seasons, cycles, rhythms that life might adapt to over billions of years. But here is where hope meets reality, where excitement collides with the brutal physics of the universe. Kepler-22b is located 635 light-years from Earth. That is closer than Kepler-452, yes, but still impossibly far by human standards. The light we see from Kepler-22b today left that planet in the year 1390, during the early Renaissance, when Leonardo da Vinci had not yet been born. Any journey there would still take millions of years with current technology. We can see this world, we can study it, we can dream about it, but we cannot touch it. Not in our lifetimes. Not in the lifetimes of our great-great-grandchildren stretching out for countless generations. Yet we study it because Kepler-22b offers tantalizing clues about what makes a planet habitable. The planet receives roughly the same amount of sunlight as Earth does. This is crucial. Too much sunlight, and the surface becomes a hellish oven. Too little, and everything freezes into a barren wasteland. Kepler-22b sits in that narrow sweet spot. Scientists estimate its surface temperatures could range from 15 to 22 degrees Celsius. That is room temperature. That is comfortable. That is the kind of temperature where water flows freely, where chemical reactions necessary for life can occur at reasonable rates, where complex organic molecules can form and persist. But temperature alone does not tell the whole story. Some scientific models suggest something deeply strange about Kepler-22b. The planet might rotate on its side. Imagine Earth tilted so far that the North Pole points almost directly at the Sun during summer. Now take that tilt to an extreme. This sideways rotation would create conditions unlike anything we experience on Earth. It would cause extreme seasonal temperature shifts that could make parts of the planet uninhabitable for months or even years at a time. Think about what this means. During one part of the year, the Northern Hemisphere might face the Sun continuously, bathing in endless daylight while temperatures soar. Meanwhile, the Southern Hemisphere would plunge into frozen darkness. Then, as the planet continues its orbit, the situation would reverse. The South would bake while the North freezes. This is not the gentle transition between summer and winter we experience on Earth. This is cosmic whiplash, environmental extremes that would challenge even the hardiest forms of life. And here is where it gets even more unsettling. Parts of the planet might face constant daylight, while other regions remain locked in perpetual darkness. Imagine living in a place where the sun never sets, where it circles endlessly around the horizon, slowly climbing higher or lower depending on the season, but never dipping below the edge of the world. Or imagine the opposite, eternal night, broken only by the faint glow of stars, with temperatures plummeting far below anything that could support liquid water. These are not conditions we are familiar with. These are not conditions we have tested. We do not know if life could adapt to such extremes. We do not know if photosynthesis could function under constant light, or if ecosystems could survive months of total darkness. We are extrapolating, guessing, hoping that the resilience of life might extend beyond what we have seen on Earth. But scientists believe Kepler-22b might have an advantage, a potential stabilizing force that could moderate these wild temperature swings, a deep global ocean. Evidence suggests this planet could be covered entirely by water, perhaps kilometers deep, with no continents, no dry land, just an endless expanse of liquid stretching from pole to pole. Oceans are thermal buffers. Water has an enormous capacity to store and release heat. On Earth, our oceans regulate climate, absorbing warmth during summer and releasing it during winter, preventing the catastrophic temperature swings that would occur on a dry planet. A global ocean on Kepler-22b could do the same thing on a much larger scale. As one hemisphere enters its scorching season, the ocean would absorb vast amounts of heat, preventing the surface from becoming uninhabitable. When that hemisphere swings into darkness and cold, the ocean would release its stored warmth, keeping temperatures above the freezing point. This is not just theoretical speculation. We see this effect on Earth every day. Coastal regions have milder climates than inland areas because the ocean moderates temperature. Islands surrounded by water rarely experience the extreme heat or cold found in the middle of continents. A planet covered entirely by ocean would be the ultimate expression of this principle, a world where liquid water itself becomes the thermostat, the climate regulator, the reason life might persist despite the chaotic rotation. But an ocean world brings its own challenges, its own questions that haunt the edges of our imagination. If there is no land, where does life begin? On Earth, the shallow margins where ocean meets shore are among the most productive ecosystems, rich in nutrients and biodiversity. Tide pools, coral reefs, coastal wetlands, these are the places where life explodes in abundance. Without continents, without shorelines, does evolution take a different path? Do creatures evolve to spend their entire existence in the open ocean, never touching solid ground because solid ground does not exist? And what about the depths? On Earth, our oceans are only a few kilometers deep at most. Light penetrates only the top few hundred meters. Below that lies the abyssal zone, the deep ocean where sunlight never reaches, where pressure is crushing, where life exists in eternal darkness, fueled by chemicals seeping from volcanic vents rather than energy from the sun. If Kepler-22b has oceans kilometers deep, what strange forms might life take in those lightless depths? These are the questions that keep scientists awake at night. These are the mysteries that drive our telescopes to peer deeper into space, our computers to model ever more complex planetary systems, our minds to stretch beyond the comfortable familiarity of Earth. Kepler-22b is hope and danger intertwined. It is a world that might sustain life, but that life would be nothing like what we know. It is a world with the right temperature, the right distance from its star, perhaps even oceans of liquid water, but it is also a world of extremes, of darkness and light, of heat and cold, of unknowns that could either nurture life or crush it. Now we must confront something far more personal, far more visceral. What would it actually feel like to stand on one of these planets? What would happen to your body if you somehow survived the impossible journey and set foot on Kepler-452b? The answer is simple and terrifying. Gravity would crush you. Kepler-452b is what astronomers call a super-Earth. It is larger than our planet, more massive, and that extra mass translates directly into stronger gravitational pull. Scientists estimate that Kepler-452b could have twice Earth's gravity. Let that number settle into your mind. Twice the gravity. Every single thing you do, every movement you make would require double the effort. Your body, built for Earth's gravity over millions of years of evolution, would suddenly weigh twice as much. Imagine waking up tomorrow and discovering you weigh double what you weigh today. If you are 70 kilograms on Earth, you would be 140 kilograms on Kepler-452b, not because you gained fat or muscle, but because the planet itself is pulling you down with twice the force. Your bones did not grow stronger overnight. Your muscles did not double in power. Yet suddenly, they must support twice the load with every breath you take, every step you attempt. Walking would become exhausting. On Earth, you barely think about putting one foot in front of the other. Your muscles have memorized the movements, calibrated perfectly for our planet's gravity. But on Kepler-452b, each step would feel like you are wearing a weighted vest that doubles your body mass. Your legs would burn with the effort. Your breathing would become labored within minutes. A casual stroll across a room would feel like hiking up a steep mountain with a heavy backpack. Jumping would be nearly impossible. On Earth, you can leap into the air with relative ease. Your muscles contract, you push against the ground, and for a brief moment, you are airborne. On Kepler-452b, that same muscular effort would barely lift you off the surface. The planet's gravity would drag you back down almost instantly. Children could not play the games they play on Earth. Athletes could not perform the feats we take for granted. The simple joy of jumping would become a distant memory, something your body could no longer achieve. But the real horror is not in the difficulty of movement. The real horror is what happens over time. Long-term survival on a super-Earth would require adaptations that push human biology to its absolute limits and possibly beyond. Your bones would experience constant strain, bearing loads they were never designed to carry. Osteoporosis, the gradual weakening of bones, could accelerate dramatically. Fractures would become common, healing would take longer, and the risk of permanent disability would skyrocket. Your muscles would need to be stronger than any human who has ever lived on Earth. Olympic weightlifters, elite soldiers, professional athletes, these individuals represent the peak of human physical conditioning on our planet. Yet, even they would struggle on Kepler-452b. Simply standing upright for extended periods would require muscular endurance beyond what any training program on Earth could prepare you for. This means any potential settlers would need years of conditioning before arrival. Not weeks, not months, years. They would need to train in artificial high-gravity environments, gradually building muscle mass and bone density to levels that might seem superhuman by Earth standards. They would need to undergo medical monitoring constantly, checking for stress fractures, cardiovascular strain, and organ damage. They would need to accept that their bodies would fundamentally change, that returning to Earth might become impossible because their reinforced frames would struggle to adapt back to lower gravity. Your internal organs would face dangers we can barely predict. Your heart, evolved to pump blood through a body under Earth's gravity, would suddenly need to work twice as hard to circulate blood against the increased pull. Blood pressure would spike. The heart muscle would thicken from the constant strain, potentially leading to cardiovascular problems. Your lungs would labor to expand your chest cavity against the increased weight of your ribs and surrounding tissue. Breathing deeply would require conscious effort rather than happening automatically. Think about your spine. Right now, as you read this, your spine supports your upper body against Earth's gravity. It compresses slightly during the day and expands at night when you lie down to sleep. On Kepler-452b, that compression would be twice as severe. Spinal discs, the cushions between your vertebrae, would be squeezed with double the force. Back pain would be universal. Herniated discs would be common. Height loss would be dramatic, not just a few millimeters, but potentially several centimeters, as your spine compacted under the relentless pull. Now consider something we rarely think about: fluid distribution in your body. On Earth, gravity pulls blood and other fluids downward, which is why your legs sometimes swell after standing for long periods. On Kepler-452b, this effect would intensify. Blood would pool in your lower extremities with far greater force. Your cardiovascular system would struggle to pump blood back up to your brain. Fainting would be a constant risk. Varicose veins would develop rapidly. Your body's entire circulatory architecture, fine-tuned over millions of years for Earth's gravity, would be operating in hostile territory. But humans are adaptable. Perhaps over generations, over thousands of years, our bodies could evolve to meet this challenge. Perhaps the children born on Kepler-452b would develop shorter, stockier builds with thicker bones and more powerful muscles. Perhaps their hearts would be larger, their blood pressure naturally higher, their skeletons reinforced with denser mineral structures. Perhaps, but this is speculation built on hope rather than evidence. Earth plants would struggle to grow normally under such conditions. The stems that easily hold leaves up to the sunlight on Earth would buckle and bend on Kepler-452b. Trees, as we know them, might be impossible. Imagine forests where nothing grows taller than a meter, because gravity prevents vertical growth. Agriculture would need complete redesign. Crops would need genetic engineering to develop stronger stalks, sturdier root systems, leaves that can photosynthesize efficiently while pressed closer to the ground. Animals, if they could survive at all, would evolve in bizarre directions. On Earth, large animals tend toward 4 legs for stability. On a super-Earth with double gravity, animals might evolve extra limbs to distribute their weight more effectively. 6 legs, 8 legs, body plans that seem alien to us but make perfect sense under crushing gravitational force. Creatures might become wider and flatter, hugging the ground to minimize the strain on their skeletons. Flight might be nearly impossible. Birds as we know them could not generate enough lift to overcome twice Earth's gravity. The skies might be empty of life, silent and still. Everyday life would feel slower, heavier, exhausting in ways we can barely comprehend. Getting out of bed would be an ordeal. Climbing stairs would be agonizing. Carrying objects would require strength training. Playing with children would leave you gasping for breath. The simple pleasures of physical existence, dancing, running, swimming, would transform into grueling challenges that test your endurance with every movement. And there would be no escape. No vacation back to Earth where you could feel light and free again. The journey takes millions of years, remember? Once you land on Kepler-452b, you are committed. Your body would adapt or it would break. Your children would know nothing else. They would be the first generation of humans shaped by alien gravity, their bones denser, their muscles stronger, their bodies forever changed by the world they inherited. This is the reality behind the excitement of discovering habitable planets. Habitability does not mean comfortable. It does not mean easy. It means that liquid water might exist, that temperatures might allow life, that an atmosphere might provide breathable air. but it says nothing about whether human bodies, fragile products of Earth-specific conditions, could survive and thrive in such an environment. Gravity is not negotiable. It is not a variable we can control. It is the fundamental force that shapes how matter interacts on planetary scales. And on super-Earths like Kepler-452b, gravity would shape us in return, moulding our bodies into forms we might not recognize, testing whether the human species is truly adaptable enough to become an interplanetary civilization. We have discussed crushing gravity, extreme temperatures, sideways rotations, and ocean worlds. But all of these factors, as dramatic as they are, depend on one fundamental question. How far is a planet from its star? This single measurement, this cosmic distance, determines almost everything about whether a world can support life as we know it. This is where the Goldilocks Zone enters the story. The name comes from the fairy tale where Goldilocks finds 3 bowls of porridge, one too hot, one too cold, and one just right. In astronomy, we apply this same principle to planets. The Goldilocks Zone, also called the habitable zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Why does liquid water matter so much? Why do scientists obsess over this one molecule, this simple combination of hydrogen and oxygen? Because water is the universal solvent of life. Every biochemical reaction we know about, every process that builds proteins, that copies DNA, that powers cells, happens in water. Life on Earth began in water. Life evolved in water for billions of years before venturing onto land. Even organisms that live in deserts carry water inside their bodies because their cells absolutely require it. Water has unique properties that make it essential. It remains liquid across a relatively wide temperature range compared to other substances. It dissolves more chemicals than almost any other liquid, allowing nutrients to flow and reactions to occur. It has unusual density properties that make ice float, which prevents oceans from freezing solid from the bottom up. Water is not just important for life. As far as we can tell, water is absolutely necessary for life, and liquid water only exists within a narrow temperature range. At 0 degrees Celsius, water freezes into ice. At 100 degrees Celsius, under standard atmospheric pressure, water boils into vapor. Between these 2 points, water flows as a liquid. This means a planet must maintain surface temperatures somewhere in this range, not everywhere on its surface perhaps, but somewhere, long enough for life to gain a foothold and evolve. Distance from a star determines temperature. Move a planet closer to its star, and the surface heats up. Move it farther away and the surface cools down. This is not complicated physics. This is basic thermodynamics that anyone can understand intuitively. You feel warmer standing near a campfire, and cooler when you step back. Planets work the same way with their stars. Earth lies perfectly inside the Goldilocks zone of our Sun. We orbit at approximately 150 million kilometers from our star, receiving exactly the right amount of energy to maintain liquid oceans across most of our surface. Our average global temperature hovers around 15 degrees Celsius. Not freezing, not boiling, just right for water to flow, for clouds to form, for rain to fall, for life to flourish in spectacular diversity. But look at our neighbours and see what happens when distance goes wrong. Venus orbits closer to the Sun than Earth does, only 108 million kilometers away. That small difference, just 42 million kilometers closer, transforms Venus into hell. Surface temperatures reach 465 degrees Celsius, hot enough to melt lead. The atmosphere is thick with carbon dioxide, creating a runaway greenhouse effect that traps heat until the planet becomes an inferno. If water ever existed on Venus, it boiled away billions of years ago. The planet is too close. The porridge is too hot. Now, look outward to Mars. The red planet orbits 228 million kilometers from the Sun, about 78 million kilometers farther than Earth. That extra distance drops temperatures catastrophically. Mars averages negative 63 degrees Celsius at its surface. Water exists there, but it is locked in polar ice caps and frozen underground. Liquid water cannot persist on the surface because the planet is too cold and the atmosphere is too thin. Mars sits at the outer edge of our Sun's habitable zone, possibly even beyond it. The porridge is too cold, Earth is just right. We sit in the comfortable middle, bathed in sunlight strong enough to keep water liquid, but not so intense that it boils away. This narrow band of cosmic real estate, this Goldilocks zone, is where astronomers focus their search for life beyond our solar system. Kepler-452b sits at a just right distance from its star. It orbits about 156 million kilometers from Kepler-452, only slightly farther than Earth's orbit around our Sun. But because Kepler-452 is nearly identical to our Sun in size and temperature, this distance translates into similar energy input. The planet receives warmth comparable to what Earth receives. It sits firmly in the Goldilocks zone of its stellar system. Kepler-22b also lies within its star's habitable zone, orbiting at a distance that allows for liquid water despite the planet's slightly different stellar environment. These are not random discoveries. NASA's Kepler missions specifically search for planets in habitable zones because those are the worlds most likely to harbour life. But here is where the story becomes more complex, more nuanced, more frustrating for those seeking simple answers. Distance alone does not guarantee habitability. The Goldilocks zone is necessary but not sufficient. A planet can sit at the perfect distance from its star and still be utterly hostile to life. Atmosphere matters enormously. Venus sits near the inner edge of our Sun's habitable zone, yet its thick carbon dioxide atmosphere creates temperatures that would incinerate any life we know. Mars might be barely inside the outer edge of the habitable zone, but its thin atmosphere cannot trap enough heat or maintain enough pressure for liquid water to exist on the surface. Earth thrives not just because of our distance from the Sun, but because our atmosphere is thick enough to retain heat, yet transparent enough to let sunlight through. Planetary mass influences everything. A planet too small cannot hold on to its atmosphere. Gases escape into space, leaving the world airless and exposed to temperature extremes. A planet too large might retain too much atmosphere, creating crushing surface pressure and runaway greenhouse effects. The planet needs to be large enough to hold water and air, but not so large that it becomes a gas giant like Jupiter. Magnetic fields protect planetary surfaces from stellar radiation. Earth's molten iron core generates a magnetic field that deflects harmful particles streaming from the Sun. Mars lost its magnetic field billions of years ago, and the solar wind has been slowly stripping away its atmosphere ever since. A planet in the Goldilocks zone without magnetic protection might lose its water to space over geological time, no matter how perfect its orbital distance. Geological activity recycles elements and regulates climate over long timescales. Earth's plate tectonics drag carbon dioxide into the mantle and release it through volcanoes, creating a natural thermostat that has kept our climate relatively stable for billions of years. A geologically dead planet might lose this regulation, allowing runaway climate change even if it starts in the habitable zone. The type of star matters too. Red dwarf stars, smaller and cooler than our Sun, have habitable zones much closer to the star. Planets in these zones might become tidally locked, with one side always facing the star in eternal daylight, while the other freezes in permanent darkness. Such worlds might still have habitable regions where conditions are just right, but they would be alien beyond our imagination. Even the star's age plays a role. Young stars often flare unpredictably, blasting nearby planets with radiation. Old stars expand as they die, pushing their habitable zones outward and potentially engulfing planets that once thrived with life. The Goldilocks zone is not static. It shifts over billions of years as stars evolve. This is why discovering Kepler-452b and Kepler-22b excites scientists so profoundly. These planets orbit Sun-like stars at Earth-like distances. They check multiple boxes on the habitability checklist, but we still do not know if they have atmospheres, we do not know if they have magnetic fields, we do not know if they have plate tectonics or stable climates, or any of the other factors that make Earth special. The Goldilocks zone is our starting point, not our destination. It tells us where to look, which of the billions of planets in our galaxy deserve closer study. It narrows the search from impossible to merely extraordinarily difficult. Finding a planet in the habitable zone is like finding a house at the right distance from town. Close enough for convenience but far enough for peace. But distance from town tells you nothing about whether the house has running water, electricity, a solid foundation, or a leaking roof. We celebrate these discoveries because they represent progress, evidence that planets capable of supporting life exist in our galaxy. But celebration must be tempered with caution, wonder balanced with skepticism. The universe is vast and strange, and simple rules like the Goldilocks Zone only capture the beginning of the complexity we face when asking whether we are alone. We have journeyed through distance and gravity, through temperature zones and liquid water. Now we arrive at the heart of human fascination with these distant worlds, the tantalizing possibility that we have found Earth's relatives in the cosmic family tree. Planets so similar to our own that scientists and journalists alike cannot resist giving them nicknames that spark imagination and hope. Kepler-452b is often called Earth's cousin. Not Earth's twin, mind you, but its cousin. This distinction matters. Cousins share family resemblance but are not identical. They have similarities that connect them, but differences that make each unique. Kepler-452b resembles Earth in crucial ways. It orbits a sun-like star at a distance that could allow liquid water. It receives similar amounts of stellar energy, and its year length suggests orbital stability that might permit life to evolve over billions of years. Some enthusiasts have nicknamed it Earth 2.0, as if this planet represents an upgrade, a second chance, a backup drive for humanity's future. The name captures public imagination perfectly. Earth 2.0 sounds like progress, like hope, like a solution to the environmental and existential challenges we face on our home world. But names can be dangerous. They can hide complexity behind simplicity. They can make distant and hostile places sound welcoming and familiar. Other astronomers playfully call Kepler-452b Coruscant, borrowing the name of the city-covered planet from Star Wars. This nickname reveals something fascinating about human psychology. We cannot help but project our stories, our myths, our dreams onto these distant worlds. We see a planet around a sun-like star and immediately imagine civilizations, cities, societies that might exist there. We fill the unknown with familiar narratives because the alternative, accepting that we might never know what truly exists on these worlds, is almost unbearable. The planet orbits its star every 385 Earth days. Stop and consider what this means. 1 year on Kepler-452b lasts only 20 days longer than 1 year on Earth. This is remarkably similar. Not identical, but close enough to suggest that seasonal patterns, if they exist, might follow rhythms somewhat familiar to us. Close enough that plants, if they evolve there, might experience growing seasons of comparable length. Close enough that any intelligent beings, should they exist, might divide their calendar into periods not drastically different from our months and seasons. This orbital period suggests something deeper and more important: long-term stability. Planets with stable orbits are less likely to experience catastrophic climate shifts. They are less likely to spiral into their stars or get flung out into interstellar space. Stability over millions and billions of years is essential for complex life to evolve. Life needs time. Evolution is not quick. It took Earth 4 billion years to go from simple single-celled organisms to the technological civilization we have today. A planet with a chaotic, unstable orbit would never give life that kind of time. The planet orbits a sun-like star, and this fact cannot be emphasized enough. Kepler-452 is not a red dwarf that might roast its planets with radiation flares. It is not a massive blue giant that burns hot and dies young. It is a G-type main sequence star, the same category as our Sun, burning steadily for billions of years with consistent energy output. This stellar stability is the foundation upon which habitability is built. Sun-like systems are ideal for habitability studies because they are the only systems we know for certain can produce life. We have exactly one example of a living world, Earth, and Earth orbits exactly one type of star, a G-type main sequence star like our Sun. Does this mean life cannot exist around other types of stars? No, but it means we start our search where we have proof of concept, where the cosmic recipe has already succeeded at least once. These similarities fuel public fascination in ways that scientific data alone never could. When NASA announces the discovery of an Earth-sized planet in the habitable zone of a Sun-like star, news organizations around the world run headlines. Social media explodes with speculation. Artists create visualizations of what these worlds might look like. Science fiction writers incorporate them into stories. People who have never looked through a telescope suddenly want to know more about exoplanets. This is the power of relatability. We connect emotionally with planets that resemble Earth because we can imagine ourselves there. We can picture standing on solid ground, looking up at a familiar-looking sun, breathing air, drinking water, perhaps even encountering alien life that evolved under conditions similar to those that shaped us. These similarities make the abstract concrete, the impossible seem almost within reach. But nicknames can hide serious dangers. Call a planet Earth 2.0 and people assume it is a paradise waiting for us. They forget about the crushing gravity we discussed earlier. They forget about the extreme seasonal temperature shifts, the potential lack of solid land, the million-year journey to get there. They forget that habitability does not mean hospitable, that a world capable of supporting microbial life might be utterly lethal to humans. The danger of anthropomorphizing these planets, of projecting human wishes onto alien realities, is that it distorts our understanding. We are not looking for a replacement Earth. We are not searching for a refuge from our problems here. We are exploring to understand the universe, to learn how common or rare life might be, to place ourselves in the proper context of cosmic evolution. Kepler-452b might have life. It might be covered in ecosystems as diverse and complex as Earth's rainforests and coral reefs, or it might be completely sterile, a rocky ball with an atmosphere but no biology, a world that met many of the conditions for life, but failed at some crucial step we do not yet understand. Both possibilities are scientifically valuable. Both teach us something profound about how the universe works. The truth is that we know very little about Kepler-452b beyond its existence, its orbit, and rough estimates of its size and mass. We do not know what its atmosphere contains. We cannot directly image its surface. We have never detected any biosignatures, any chemical traces that would indicate life. Everything else is inference, extrapolation, educated guessing based on the limited data we can gather from 1,800 light-years away. This should not diminish our excitement. If anything, the uncertainty should amplify it. We stand at the edge of a cosmic mystery, knowing just enough to ask better questions but not enough to answer them. Future telescopes, more sensitive instruments, new analytical techniques might reveal more. The James Webb Space Telescope and future missions could potentially analyze the atmospheres of planets like Kepler-452b, searching for oxygen, methane, water vapor, chemicals that might indicate biological processes. But even if we learn more, even if we confirm that Kepler-452b has an oxygen-rich atmosphere and liquid water on its surface, even if every measurement suggests it could support life, we still face the insurmountable barrier of distance. We cannot go there. We cannot land rovers there. We cannot collect samples. We can only observe from afar, gathering photons that have traveled for nearly 2 millennia to reach our instruments. This is the bittersweet reality of exoplanet science. Every discovery is also a reminder of our cosmic isolation. We find worlds that might harbour life, worlds that might be beautiful beyond imagination, worlds that might answer the most profound questions humanity has ever asked, and we find them forever out of reach, separated by distances that mock our fastest rockets and longest lifespans. Yet we keep searching, we keep building better telescopes, we keep analysing data, refining models, pushing the boundaries of what we can detect and understand. Because the alternative, accepting ignorance, choosing not to look, is fundamentally opposed to human nature. We are explorers. We are questioners. We are a species that looks at the stars and refuses to accept that they must remain forever beyond our understanding. Kepler-452b and Kepler-22b are not destinations. They are not solutions to Earth's problems. They are not proof that the universe is friendly to life. They are clues, breadcrumbs leading us toward deeper knowledge about how planets form, how stars evolve, how rare or common life might be in the cosmos. They are mirrors in which we see reflections of our own world, reminding us how special Earth is even as they hint that other special places might exist. The nicknames will continue, the public fascination will endure, and scientists will keep studying these distant cousins of Earth, not because we can ever visit them, but because understanding them helps us understand ourselves, our origins, and our place in a universe far stranger and more wonderful than our ancestors ever imagined. We have travelled through 5 parts of this cosmic journey, exploring distant stars, analysing alien worlds, confronting crushing gravity, understanding habitable zones, and grappling with the nicknames we give to planets that spark our imagination. Now, we must face the ultimate truth, the lesson that Kepler-452b and Kepler-22b teach us with unforgiving clarity. Earth-like conditions are astonishingly rare in the universe. This realization should shake you to your core. We have discovered thousands of exoplanets. Thousands. Our galaxy alone contains an estimated 100 billion planets. With those numbers, you might assume Earth-like worlds are common, scattered throughout the cosmos like grains of sand on a beach. But the more we learn, the more we realize how extraordinary our home planet truly is. Being in the habitable zone is only the first requirement, not the final answer. This cannot be stressed enough. When scientists announce they have found a planet in the Goldilocks Zone, news headlines scream about potential new homes for humanity, about Earth 2.0, about the discovery of alien life. But orbital distance is merely the starting gate, not the finish line. It is the minimum entry requirement to a competition where thousands of other factors determine success or failure. Think about everything that must align perfectly for a world to be truly habitable. The planet needs the right distance from its star to maintain liquid water. Yes, we have established this. But it also needs the right mass to hold an atmosphere without becoming a gas giant. It needs the right atmospheric composition to trap heat without creating a runaway greenhouse effect like Venus. It needs a magnetic field to deflect radiation. It needs plate tectonics to recycle elements and regulate climate. It needs a large moon to stabilize its axial tilt and prevent chaotic climate swings. It needs to orbit a stable star that does not produce lethal radiation flares. Every single one of these requirements is rare. Stack them together, and the probability of finding a world that meets all of them simultaneously drops to almost nothing. Kepler-452b sits in the habitable zone, orbits a sun-like star, and has an orbital period similar to Earth's year. Excellent. But we do not know if it has a magnetic field. We do not know its atmospheric composition. We do not know if it has plate tectonics. We are celebrating a planet that meets perhaps 3 criteria out of dozens necessary for true habitability. Gravity alone could make long-term human survival extremely difficult, as we explored in gruesome detail earlier. Double Earth's gravity means double the strain on every bone, every muscle, every organ in your body. It means a lifetime of exhaustion, of cardiovascular stress, of skeletal compression. It means children born on Kepler-452b would develop bodies fundamentally different from ours, adapted to crushing weight, perhaps unable to ever return to Earth without their bones shattering under what we consider normal conditions. But gravity is just one challenge among many. Rotation, atmosphere, and oceans can turn a seemingly perfect planet hostile in ways we barely understand. Kepler-22b might rotate on its side, creating extreme seasonal temperature shifts that make large portions of the planet uninhabitable for months at a time. Even if it has a global ocean to moderate temperatures, we do not know how effective that moderation would be. We do not know if the ocean would freeze solid during dark seasons or boil during bright ones. Atmosphere is destiny for any planet. Earth's atmosphere is 78% nitrogen, 21% oxygen, and trace amounts of other gases including carbon dioxide. This exact mixture took billions of years to develop, shaped by photosynthetic organisms that gradually converted carbon dioxide into oxygen. Without life, Earth's atmosphere would look completely different, probably resembling the carbon dioxide-rich atmospheres of Venus or Mars. If Kepler-452b or Kepler-22b have atmospheres, what are they made of? Nitrogen and oxygen like ours? Carbon dioxide and sulfuric acid like Venus? Methane and ammonia like the gas giants? We do not know. We have no way to know with current technology. Even rocky planets can become unlivable, as Venus proves with terrifying effectiveness. Venus is nearly Earth's twin in size and mass. It orbits within what some models consider the inner edge of our Sun's habitable zone. It should be a paradise. Instead, it is hell incarnate. Surface temperatures melt lead. Atmospheric pressure crushes like being 900 meters underwater. Clouds of sulfuric acid rain down, though the droplets evaporate before reaching the ground because it is too hot for liquid to exist. Venus demonstrates that being rocky, being the right size, even being in or near the habitable zone, guarantees absolutely nothing. What went wrong with Venus? Scientists believe it experienced a runaway greenhouse effect early in its history. Water vapor in the atmosphere trapped heat, which caused more water to evaporate, which trapped more heat, creating a feedback loop that spiraled out of control until the oceans boiled away completely. The carbon dioxide that on Earth gets locked in rocks and ocean sediments remained in Venus's atmosphere, thickening it, heating it, transforming the planet into an oven that has been baking for billions of years. Could the same thing happen to Kepler-452b or Kepler-22b? Absolutely. We have no idea if these planets avoided Venus's fate. We have no idea if their atmospheres are thick or thin, stable or chaotic, breathable or toxic. Distance from the star matters, but atmospheric chemistry determines actual outcomes. Oceans may stabilize climate, but they also create new unknowns that complicate everything. A global ocean on Kepler-22b could moderate temperature extremes, yes, but it also means no land, no continents, no shallow coastal zones where Earth's most diverse ecosystems thrive. It means any life that evolved there would be entirely aquatic, adapted to perpetual swimming, possibly dwelling in depths we cannot fathom. It means colonization by humans would require floating cities or underwater habitats, engineering challenges that make settling Mars look simple by comparison. And what lies beneath those hypothetical oceans? On Earth, our ocean floors are geologically active, with volcanic vents pumping minerals and heat into the water, supporting ecosystems that survive without sunlight. Does Kepler-22b have similar geology, or are its ocean depths cold, dark, and sterile? We celebrate the possibility of water without acknowledging that liquid water alone does not guarantee life, only the potential for it. Distance makes exploration a centuries-long gamble, even at light speed. This is the cruelest joke the universe plays on us. We find these tantalizing worlds, these potential cousins of Earth, and they are forever unreachable. Kepler-22b is 635 light-years away. Even if we could build a spacecraft that travels at the speed of light, which physics says is impossible for anything with mass, the journey would take 635 years. Generations would be born, live their entire lives, and die on that spacecraft before it arrived. And that is assuming light-speed travel, which remains pure fantasy with our current understanding of physics. Human bodies are finely tuned to Earth and struggle outside it in ways that become more apparent the more we study space travel. Astronauts on the International Space Station, orbiting just 400 kilometers above Earth's surface, experience bone loss, muscle atrophy, vision problems, and immune system dysfunction after just months in microgravity. Mars colonists would face similar issues plus radiation exposure that could cause cancer. And those challenges pale compared to what awaits on a super-Earth with double gravity, or a planet with extreme seasonal shifts, or a world with atmospheric chemistry hostile to human biochemistry. These discoveries reshape how we define a second Earth. There is no Earth 2.0. There is only Earth, and there are planets that superficially resemble some of Earth's characteristics, while differing in countless other ways. The term second Earth implies replaceability, as if planets are interchangeable parts in a cosmic machine. They are not. Each world is unique, shaped by its own history, its own chemistry, its own evolution. Kepler-452b is not a second Earth. It is the first and only Kepler-452b, a world unto itself that we are only beginning to understand. They remind us that Earth is not just habitable, it is exceptionally balanced in ways we take for granted until we examine other worlds. Our planet orbits at exactly the right distance from a stable star. We have a large moon that stabilizes our axial tilt, preventing wild climate swings. We have plate tectonics that regulate atmospheric carbon dioxide over geological timescales. We have a magnetic field generated by a molten iron core that shields us from solar radiation. We have an atmosphere thick enough to retain heat, but transparent enough to allow sunlight through. We have oceans that cover 70% of our surface, moderating temperatures and driving weather patterns. Every single one of these features is essential. Remove any one, and Earth becomes hostile to life as we know it. The fact that all of them exist together on one planet is not luck. It is the result of billions of years of planetary evolution, of countless cosmic accidents and near misses that somehow produced the exact conditions necessary for complex life to arise and persist. The universe may be full of candidates, but true homes are rare beyond our ability to comprehend. We have found thousands of exoplanets and exactly one that we know supports life, Earth. This ratio should humble us. It should make us appreciate what we have. It should make us desperate to protect the only planet we know for certain can sustain us. Every new exoplanet discovered deepens both our hope and our humility. Hope because each discovery proves planets are common, that worlds orbiting distant stars are not fantasy, but reality. Humility because each discovery also reveals how specific, how precise, how improbable Earth's conditions truly are. We are not special because we are the only life in the universe. We may very well not be, but we are special because we exist on a planet that balances so many variables so perfectly that complex intelligent life could evolve over billions of years. Kepler-452b and Kepler-22b are not destinations. They are mirrors forcing us to see ourselves more clearly. They show us that finding habitable planets is not the challenge. Finding planets where humans could actually survive and thrive is monumentally difficult. They teach us that space exploration is not about escaping Earth, but about understanding how extraordinary Earth is and why we must cherish it.